Hi, uh, good afternoon. Just a few minutes from now. Uh, this is myself, Sriram Pore. I'm associate VP of Technologies at MSys Technologies. I would quickly like to introduce Divyank and MSys a bit. MSys is a fastest growing storage services company, primarily, as I said, more into the storage domain or data center technologies from storage, network, virtualization, and cloud. Of course, we get into AI, ML, and how that can feed into these data center technologies and stuff, and others like DevOps and automation. Having said about that, I'd like to introduce Divyank. Divyank is our technical architect. He would like to bring at least a couple of decades of his experience into storage domain. He has like 4 patents on his names, and he would like to bring in deep learning or machine learning, how it can be used in data center technologies, primarily into storage space, to come up with recommendation engines. And I'll leave it to Divyank here.
Okay.
Thanks.
So let me start with some of the problems description that we started to start with. So yeah, so one of the critical problems that one of our customers had is their clients were constantly, trying to figure out as to what would happen if they happen to change some things in their service provider. Some of the examples being, if we migrated some of the extents, how much my other clients will suffer in terms of SLAs, or maybe what milliseconds impact will that happen, which meant they wanted to look ahead. And this problem is not new, and we see that capacity management have some of these problems, similar problems. But as you'll see how we progressed about solving this problem, where we could adequately advise our clients a priori about their investments, or about how their data centers component should improve, or in terms of what is the bottleneck that's happening. So just give you a brief outline as to how what's the basic framework of this. Here we are only targeting read for primarily because now what has happened is writes have started to come into, their latencies are slowly decreasing, and it's the read that requires us to pull up all the data from different caches. That is the problem. So let's see. So we start with a generic engine that actually accepts the requests, and this is the actually the box that receives the request and actually completes the request in terms of actual data flowing out through this particular layer. There's a admit thread that actually sees what's the back pressure behind. For example, there could be SSDs, there could be disks, and what is the impact on their queues. And based on that, it will either queue or restrict the clients for more IOs, or it will allow them to go through. And subsequently, it will push a read request to the component. And the read, depending upon the data, whether it lies in its cache, it will give it, or else it will actually pull up the data from the real data stores, or the cold data, as they say. So so a basic flow happens like you have a thread that admits the process and the request, and those requests are broken down into operations. Typically, you could have a large size request that broke down into many read requests for subsequent components. And sometimes those operations might contend for locks, and they may experience wait times. At times, they may be waiting for some other request getting queued up. So some of the metrics that are important in this particular analysis is request latencies at each component level. So if you see this particular thread, it has got an wait/latency component at each layer, which means depending upon how big or small your request is, and what is the state of that request dependent objects, is will drive the actual latency that happens at the end. So I'm just trying to explore the problem space, and if you see, you could drive this problem in terms of a classification problem, where you say, okay, any request that suffers a 10% degradation, let me classify as class 3, and a 20% degradation, let me classify as a class 4, and if I better my performance by 5%, I'm class 2, and by 10% if I better myself, it's class 1. So if I happen to collect all the data that goes on in my storage provider, and then I classify my output in that fashion, that's one way to look at the problem. Another way could be, I just take pure numbers and say, okay, if I am 100 nanoseconds or 50 nanoseconds or 20 nanoseconds, just take pure numbers and not the cardinal values or ordinal values to classify them. But then when I look at the problem from a different perspective, if you see a storage box is itself a box of boxes. There is a cache element there, there's a disk, and all these objects have queues and they have their own internal states. A classic example is like if you see a SSD, if a GC is going on, its performance happens to get impacted immensely. And so what can we do about it? Can we predict, so there are two aspects here. Can we predict the next GC that could happen on the SSD? So there are some work going around by various SSD providers in that aspect to be able to give their clients an assessment that, okay, there's a GC going around, why don't you get the data from somewhere else? And there is sufficient experience in storage world where we say a particular data organization helps us with a particular scenario. So it became a queue modeling problem. Can I model it with queues? And then can we model it as a Poisson process? So one thought process was, why not model it as a Poisson process? For example, if we take a load and we say, and we describe this load, okay, this is my database load, and when does all the logging or aggregation or a merge thing come to me? And that could happen depending upon how you have tuned your box. For say every 10 minutes or let's say a minute, you run a garbage collector which will free all your boxes, all your unused data. So if we can model that way, and is it all of the above? So probably in bits and pieces you will see some of these getting utilized and some of them helping us. Some of the problems we thought how we can go about it is there's linear regression. So let me just talk a little bit about linear regression. It's a very popular term where you say, what if my output variable is linearly dependent upon my input variables? Most of you, I don't expect you to be really experts in statistics, but think about it like your axes, the X, Y, and Z axis, and think about the projection of the Y axis on the X or the projection of Y axis on the Z. And you'll see the projection of these axes on each other is 0. And that meant any point in this room can be accurately depicted by its components in each of these axes. This is very important. What happened if my axes were tilted? For example, I have a slanted axis and I want to do a projection of those slanted axes on these three, and I want to define my point based on those slanted axes. It won't be possible, and so what you will do is you'll take the projection of an independent variable, which I want to say is linear regression is only possible when your objects are not related. Their projection on each of them has to be 0, which means they have to have 0 correlations. A look at our problem that we want to see is, we see quite of relationships. If you see and as we'll see, the data will tell you that it's no brainer that our wait latencies will increase if our framework thread latency increases. We can't probably say for sure whether it's linear, polynomial, radial, but we can certainly say that it's related and it comes into action. Similarly, coming about the second approach is naive Bayesian classification. A small intro on naive Bayesian is what happens if, what is the probability Y will happen knowing that A has happened. A small peek into this in our world is, I would expect my latencies to improve if I know my data cache module has brought in data. To loosely say that if my extent has recently been refurbished, it's high likely that my next latencies would be dependent upon the top two components, which is the socket component or the whenever they get the time or their. So what I'm saying is conditional probability. So what happens? How if my requests are coming in this extent and it is recently refurbished, it's likely that my latencies will not go to the framework thread and its response would be much better. Another approach, if you like to think like it's a multi-resource queue problem. Okay, so that's a classic problem where you say you are dependent upon n resources and each resource is modeled as a queue. So expected value of return from each queue you can model as some function. So that was one that's entirely very mathematical and statistical in nature. Another important aspect that you won't want to look out is ARIMA. I'll just declassify the jargons, which is auto regression integrated moving average. But apart from it, it's a typically time varying data, which means if your curve is like this, you pretty much know that the nth output is highly dependent upon n minus 1th data. So if I know what my data is today, I know it is, if my data is like that, for example, if I earn 2 rupees tomorrow and in 10 days time I make it 20, so I am pretty much low in 20 days time, I might again improve it by the same proportion as I had, plus minus some errors. So that is about time based forecasting or typically ARIMA. ARIMA has problems because it has a lot of assumptions about the data that it wants to operate on, and I will get to why we can't do. Then we thought it's actually predictive state modeling. Now, the cool idea about predictive state modeling is your output is entirely dependent upon the state where the system currently is. I'll give you an example. If you are on a degraded state, for example, you have a 2 or 4 controller, 4 node controller, and you are probably running on a degraded state, which means one of your nodes is down or of your IO path, then you clearly know that your IO times are going to suffer, which essentially means if there is a way I can divide my states in such a manner that then I would be able to closely predict what my next IO latency or what my Mbps output would be. And we saw that, our storage boxes are really have a state in themselves, and that state actually defines their output to the clients. And if we were able to predict the states, we would pretty much be able to predict the outcomes. Then the final approaches that we came about is these standard statistical mathematics is actually good when you don't have all the data. If you're going to work on some sample of the data, it's perfectly fine. But when your data is unsampled and it is correlated as well, then it becomes very difficult for us to actually classify the problem or come up with a solution for either of them. Then later on we further investigated and we saw that neural networks with states is the way we want to go forward. And then neural networks with states with time varying capacity is actually the resolution for. So basic statistics, I'll skip in interest of time. So basically that we discussed as to are the variables dependent is one of the key aspects that we want to see. Does the cost response to delta changes, how does it change with the change in dependent variables? How's your error modeling happening? Is your function linear, non-linear? Which means, do you want to say if we happen to log transform? So essentially all predictions in classical statistics happens over a line. If you are not able to model a line, you will say, let me take a log of it. Does it make a line? If it makes a line, I can form a mathematics equation which is precise enough to actually predict my object, whether it's going to be this side of the classifier or the other side. Does the response vary from time? The response essentially means the response of the black box that we were trying to create. What are the different, so one of the important aspects here is what is the sample that you're going to take and how are you going to treat the sample differently at each iteration. We'll come back to this in a little bit minute. Yeah. So a small analysis that we did with this particular graph is, if you see the graphs on this side. Oh. So if you see this, that's the internal average throughput, which means how much the system had to struggle to give you a Mbps. And you can see it's pretty much straight line, and it's highly correlated data in that aspect. Coming back to the second graph, if you see the disk throughput, which means how much the disk has struggled to give you an internal average throughput, or the output to the client, is typically linear. Look at how it has suffered, because typically systems don't do synchronously. What storage controllers do is they acknowledge a request, they merge a request, and send an asynchronous request to the lower end, and then let the data come back to them. If you can see the relationships of that data with respect to the read MBS, it's pretty much linear, but you see some aberrations there. Similarly, the average throughput normalized IOPS. I'll just give a small hint about what normalized IOPS is. You have an IOPS assessment, then you your apps could be 4K, 32K, 128K, 64K. Depending upon what your IO depth are and what is the size of your IO, you use that as a, you give different IOs, but you normalize the IOPS so that you get a cool figure where you say, okay, this is what my systems can handle. And the last one is actually very important, and that is the CPU fraction dedicated to this particular client. So almost all storage controllers have this concept of quality of service that they want to render to their clients. And one of the classical ways is they allocate a thread, meaning, okay, per client threading you want, or you want it per pool based, or you want disk based. I mean, what volume you are going to give it to them. And if you see the spread of this QoS, you see unusually high QoS CPU utilization for a not so much high throughput. And for a higher throughput, the QoS suddenly went down. And that typically if you can see the two clusters, you have a cluster here and a cluster there. And that typically sees that you were doing something else. The system, actually it's just a thread which might not have got the CPU, which meant the system was doing something else, hence it was maintaining a state. And this analysis tells us that linear regression is obviously not the right way. The plot of latency plot has a similar feature, and it's very cluttered, but one thing is very clear, that there is a positive correlation of the data. As the IO latency improves, so if you see the resource average millisecond taken, if it's higher, you have a higher average latency. Any queries about the data? Because we spent close to 1.5 months to just understand what that data means to us and what model can we fit to it. Because once understanding the data is clear, then we can come up with a model that we want to do. So then we come to the system weight matrix, and you can see clearly a stepped approach. There is no way a linear or regression could have helped us. I believe SVMs could have helped us, but they would have complicated the model. You can see the stepped approach that's coming up clearly as the locking millisecond has improved. So, so this is one graph. You can see this. So this is how our actors are busy doing work. And this particular graph is demonstration of how busy our actor is. If you see this red graph, the red one is the actually our which is taking data and sending data, which is taking request and sending data back to the clients. And if you see, it's not too much busy. If you see, it has a spiked nature, which means there could be 4K writes coming too much very quickly. The faster you accept the request and dispense it back to a client, the client is able to again give us back those requests back. And then there is a steady state. But if you see this green line, so green line is the read, and if you see, the green line is almost non-existent in the earlier phase. We'll come to it why. but if you can just notice the few patterns, is green line is around 0 or something, and then suddenly it shoots up. And then this is the read thread, the read actor that is actually responsible for getting us all the data. And yeah, I just splattered over it, the QS impact. So you can see this. Yeah, you see this? You can see this cluster, this getting clustered at this area, this QS getting clustered at this area, which meant a considerable amount of CPU is being taken up by the read threads at this end, which typically lets us to believe, oh, can you see the green dots that I'm trying to, the blue ones are the QS, and the green line is, and this is the cluster. If you can see this one cluster, this is another cluster, you can see this is one cluster, this is one cluster. So these are the QS clusters. And let me tell you, we repeated the experiment just twice. So this spike is same as this spike, right? If you see this spike. So this is the same date, same style workloads that's getting repeated. So this gave us some hints as to there is repeatability in the system's behavior, which meant again back to which cemented our thought process that there is system has some residual information that is trying to communicate it back to us. If you see the pattern of this particular line, this red line, which is this one, I mean, this red line, yeah. If you see the pattern of that red line is pretty much similar. Okay, so this is the classification of the IOs that we sent to the, so these are different types of IOs, and and if you see each of these cluster is represented. So if I draw a line, straight line, this is one type of IO, and typically all, let's say 4K reads or 8K reads or 16K reads and 64K reads. So again, and if you see the step is getting repeated, it didn't continue for long because this kind of test did not run, or let's say there's one test that did not run for some reason. But the idea here is there is some kind of a repeatability in the system's response, and that encouraged us further that there is way we can, we can actually simulate the model. Some of the observations that we saw here was that it's in low dimensional space, which means there are only 3-4 things that we want to, we are saying it's changing, Mbps, IOPS, and latency. And but we also see that there is significant parameter sharing. If I want to just say what parameter sharing is, what leads to say that the IO latency at this stage also remains same at this stage. If you see this and this, so across systems, if you see there is, and if you see some of the values, this values are all clustered together. This is an isolated value, understood, but there is certain clustering around it. This means if one request is able to share its response times with other, it means that there is significant amount of parameter sharing or state sharing happening. So parameters are sharing across histories. Some of the models that come to our mind for traditional statisticians, it would be K-state Markov model. So a Markov model is nothing but it attempts to say that if you are in a state X, you will always get an output Y. If you are in a state Z, you will get an output Y dash, which means you can predict what your response is going to be based on which state you are in. And we could say, we just didn't want to say we are just one state, and because there were many resources and there are various combinations of the resources, so we just didn't know what state to move them to. There is significant study done around predictive state representative modeling, and this is for advanced statistics. We also saw that it's not that only it is dependent upon state, it's also dependent upon time. So there is a time, there is a aging aspect also happening in the system, and To name a few, a 4K loaded cache might run down slower than a 128K cache. So we wanted to capture this aspect in terms of our model. And then finally, we thought a stateful neural model is one of the better ways to model our, and we'll see how we desperately failed in that attempt, and we went on and on to make it into a stateful inferential neural network model. So the first idea is you try to develop a state, and the second time is you say what is your rate of change of state, which means can you develop an inferential model on it. So just to bring you some basics here is, this is my state. Okay, so this ST is your state, and remind you the weights are actually your input parameters. I mean, so AX plus BY plus CZ, so these weights are ABCs, and your XYZ are your samples, and your YT is going to be milliseconds and something, and your X that you see here is, you can say that it is an outcome of your change of state, which will again be fed back to the system in time, which means that XT could be like your classification of your how good your model is, or let's say how many times did you actually make your made your device run at what Mbps. For example, let's say if your internal device was running at 10 Mbps, you had X millisecond, and when the internal device was running at 5 millisecond, you might have X dash, and you might say that okay, my X dash is much lesser than X, okay, which is a representative of this X matrix, okay. And these U and V are block box transformational functions. I'll just give you a brief on time sensitive models. This is, mind you, a time sensitive model, but we are looking for time sensitive state models. And if you see here, ARIMA is the traditional model. It is time sensitive, but it is memoryless. For example, it has no clue as to if my state of the system was P at n-1, then my output should change to Z versus when it was P. So we'll come to that later. But ARIMA is memoryless, just remember that. If you have a function which will say it is just twice, so if today I was earning 10 rupees, in 10 days time I would be earning 20 rupees, something like that. Neural networks are not necessarily time sensitive, but neural networks are touted to do everything for you. So they are not time sensitive, but they are such a black box that if you started to feed time as an input to your neural box, it might as well adapt to that circumstance and give you some numbers. How true, how good, depends upon what model you actually settle to. RNNs are a variation of neural networks where you say your time changes with your output changes with time, and at t minus, so you have state 1, state 2, state 3, and your back propagation actually rolls back all the time. So you can unroll the whole network, tn-1 and things. RNNs with LSTMs. LSTMs are long short-term memory. So when you say long short-term memory is so like your flip-flops, we had experience with our flip-flops where it can store digits as 0 and 1s. You can take that further where LSTMs have a gate where it can remember a pattern or a function or a triggering point. And there is another gate which can say you can attention or you can forget it. So LSTMs are blessed with some space in memory where they can remember a pattern, and where they can you have the flexibility to tell them whether to forget the pattern or to remember the pattern. They also come in various, but then if you can see the correlation between a normal input-output gate that you had flip-flops and with LSTMs, you will appreciate how you can build more complex models on top of them, and that's what typically bidirectional LSTMs or eco-state networks are. I think I'll gloss over these because I've already talked about ARIMA's pros and cons, and we obviously know that we don't know the lag. So in ARIMA models, you need to know the lag, which means I need to know how much lag is my repeating business is happening. For example, if I earn ₹1, I should know after 10 days it's going to double or triple. So that to be able to predict on after next 10 days what's going to be my output. So you need to know the lag, and if it's moving averages are typically, when you have differences that you want to sum up. Some of the important things about neural networks, but I'll talk about more what the problem it has. It does not have any insight why it did not work, and it cannot remember, and unless you give time series to neural network, and giving time is a very bad idea to neural networks, for the simple reason neural networks works best when it's standardized, and you can't standardize time samples. So they obviously do not have any mechanism to predict time series data. This is what we want to do actually. So our goal is very clear, that we want to build a context sensitive time varying model where my state at t minus 1, my state at t depends upon t minus 1. However, when I want to correct my model, my response or error in response should be able to correct it at t minus 1. Are we clear? It might sound very complex, but the idea is, if you see these red arrows, these are nothing but corrections. So these corrections have to flow. So which means your RNN has to be unrolled, what you did n t minus 1. But when you back propagate, so you should be able to correct the weights. So it's all about what weights are going to give you what results. Okay. As we saw, RNNs give us this flexibility of time variation because it memorizes sequences very well. So it has a dynamic state. By dynamic state, I want to say that it's not static, and the hidden Markov models or hidden states were saying that, okay, if you have a state x, your output is going to be x dash or y dash. But RNNs are not inductive. For example, if I knew that my sequence is A, B, B, then in the next sequence, all I want to learn is B has to be improved twice. So it won't say if it is ACC, it won't be able to predict that particular sequence. If it is ABB, it's able to predict that. So it's not very intelligent, and RNNs suffer from two problems. One is the training data, it needs quite huge, and other is the vanishing and exploding gradients. I'll just give a minute or two on vanishing and gradient problem. The idea is when you do back propagation, yeah. So what happens? The corrections that happen at this, the corrections that happen at the earlier stage are different in measure than what they happen at the later stage. Okay, so that causes the vanishing and the exploding gradient problem, because the delta varies and the learning rate is so very important in this particular thing. And results do vary depending upon models chosen. This is an important model and is the building block for our what we did for this particular customer. So LSTMs are integrators of the sequence learning. So LSTMs are mostly used in our language text processing, where they actually remember how your translation has happened or what you actually mean. So these guys are not able to also problem with these guys when we try to use them on storage problem was that we did not want them to learn all the things, and that way the memory cells would explode and our time would be taken much larger. And actually LSTMs also work very bad when they are correlated. So what we did was we created stacked LSTMs where we had models working on different sets of data for different inputs. And one of the important trade-offs that we saw was fewer neurons versus adding more layers. So this is how you can tune your model. I think this results will tell you much better. So if you see this blue line, this is your simple LSTMs, and you see its error losses are converging after a longer time, and there are still 6 significant loss. And the variational LSTMs is where we try to add some non-linearity by adding some dropout layers on them, and they help us converge. They are much better. And if you see this stacked LSTMs, you see this incline here. So our job ideally is to ensure that this incline is this way, and this is actually a result of when we add lot of LSTMs and dense networks. I'll actually give you my GitHub ID where you can actually see the models, and then you can actually play around and see how it actually works. So future scope for this particular implementation is actually using ESN networks. I'll just give you a brief network and why I related very well with this ESN networks. So eco-state networks are actually where your input states change non-linearly while your output are changing linearly. If you go back to the, if you go back to these slides, right, you can see the many times there is a non-linearity in behavior, wherein the state change behavior is non-linear, and there is linearity in some aspects. So so that's the reason we see that eco-state network is the next way we can model this. The reason we still leave it as a scope because there is no model that is perfect. It's just that some models work better for you and some models don't. Any questions at this point in time? No? No time for questions. I just wanted you to see this, okay? So if you're aware with series, Fourier series and inverse Fourier transforms, right? In our maths we had Fourier series, and you could see that how inverse Fourier would actually extract the base things for us. Similarly, if you can model stacked models versus simpler models. So you can use various stacked models and give their inputs to another's, or you can convolve different functions based on that. So I think that is the key takeaway. You can build smaller models and stack them together and work out. Some of the Q analysis, this is a laws that we had at play that we said, and it's basically about, yeah. So you can, if this PDF is out, you can use this collab worksheet for your use, and it has some models. I think that's all about it.